then I need to construct the next state by this Hamiltonian, by maybe not maybe by applying this Hamiltonian into the first initial moment state. Maybe I call initial state, and then I have the second state is sigma d times plus. So if I just use these two states to define my state, so now I have two states, and then I use these two states to contrast the following matrices, and and then I solve this differential equation. I can know if I pick these two states as my answers, I can see what happened if I only pick these two answer states. And if finally if your Hamiltonian, if your expectation of Hamiltonian didn't show what you want, for example, you can benchmark the exact result with what you pick the two state case. And if it didn't happen to fit the exact solutions, you can pick more states. For example, you can pick the so-called two moment state by applying the Hamiltonian twice to the zero moment state, or I say initial state. And then in this situation, you have three maybe I say three states to construct your answers, and you can follow the same guideline and solve this equation and solve the evolution of Hamiltonian. And maybe it will have some, maybe its error will smaller than the previous case. So in definition is that you can systematically construct many moment states, and you can collect it together, and it is denoted to the CK is called cumulative K moment state. And you can construct these states by, as I say, the unitary parts of the unitary part. And the zero moment state is, I say, is first moment is a zero moment state because you didn't apply any unitary on it. And maybe you that this unitary is from the Hamiltonian, from this Hamiltonian, is U. And then you can construct the one moment state from this Hamiltonian and apply it one times. So maybe for example, if you only have one turn, so your one moment state is only U times the phi 0. And if you want to construct two moment state, you can just apply it twice. But in this toy example, you can see it has the sigma d, the square is once, so it comes back to the first moment state because it is very easy example. But if you consider non-trivial example, it will not come back to the zero moment state. So you can follow this. Okay.
May I ask a question?
Okay.
So why do you need to define a K moment state? So your moment state is how many times you apply the unitary U onto the psi 0, right?
Yeah.
So the U is arbitrarily chosen from the R unitary state, or either is the the same U.
If you have two terms, you need to combine them all together. Do you make sense?
So suppose it's two U1 and U2, and what when you mention a two moment state, you means the same U1 or either U
all combined together. So you have U1 square phi 0, U2 square phi 0, and U1 U2 U1.
So all these are two moment state. Okay.
Yeah. And you combine them together to fit into the answers. So you have many moments, many answers, moment states. Yeah.
Okay.
Yeah.
Okay.
And,
thanks.
Yeah. So it is a systematic way to construct your answers. Compared to the previous variational quantum eigensolver, it didn't have some systematic way to make answers. So, and this reminds me that the paper tells me that it reminds you the chiral subspace method is it's very similar because the B in this algorithm is just the zero moment state, and you apply it iteratively, and you combine them all together to span these spaces. So it's very like a chiral subspace method. And after you after you select your answers, you need to calculate you need to use these answers to calculate these two matrices, and basically you sorry, maybe I won't maybe you use some Hon-Hai test to construct the epsilon matrix and D matrix, but this Hon-Hai test is challenging in the niche Q area because the hardware isn't good enough. So in this paper, they have some claim that sorry. Oh, sorry. They have, maybe I skip this. So they have some claim that you can replace the Hon-Hai test to some direct measurement of the because we know that Hon-Hai test is some indirect measurement, and they constraints. Sorry. Here. So they have some claim that they can replace the Hon-Hai test to the direct measurement of the Pauli term. Because there's some constraint. So if, for example, your Hamiltonian have only the Pauli terms, and you can replace the Hon-Hai test to some direct measurements, and you can, if you're interested, you can check the paper, or where is my, sorry, maybe I cut. So yeah, I can say that there are some paper tell the technique of how to replace the Hon-Hai test to the direct measurement of the Pauli terms. So maybe I just skip that because I haven't find my slide. Oh, sorry, here. So if you are interested, you can see this paper to see how to replace the Hon-Hai test to the direct measurements. But there's maybe too detailed, so I need to skip this part. So after you use that technique to calculate the two matrices, the quantum computation is the quantum computation is over, and you use the outcome of the quantum computation to define this differential equation, and you solve it in the classical computer, and so you get the evolution of this alpha, and you can see the evolution of the expectation value of the Hamiltonian. Yeah. So this example show you that they only use because it's a very simple model. They use only two states to construct these answers, and you follow the algorithm and solve how to evolve this alpha 1 and alpha 0t, and you can see that this only because it's very simple Hamiltonian. So you only need to one moment. You only need to accumulate 0 moment state and 1 moment state to evolve the sigma x matrices. You can see that if it fits the exact solution, but it's very easy, simple case. So let me move to some even more complicated case. So in this example in this example, its answers is only single qubit state. It's plus states, so it's very I think it's a very toy model. Yeah. It's like a Hon-Hai model. And in this example, they use 12 qubit answers, and the layer is 200 layers. This block is defined one layer, and repeats it 200 times. So in this situation, it's very hard, as I say in the Baron-Pentos paper, because it's 12 qubits, and its layer is 200 layer is gradient is, I think it's small enough and it's very hard to train in the variational quantum circuit. So in this ansatz, it's 12 qubits and 200 layers, and we use it as a 0 moment state and apply this Hamiltonian to construct the further 1 moment and 2 moment states. But in this example, it only need one moment state. It means that you apply this Hamiltonian once to get the one moment state and use 0 moment state and 1 moment state to follow the algorithm and see the evolution of sigma s. It can match the exact solution. But I think it's some I think it's better to not to show this figure, but to show the accuracy is much better because it only, I think it's not 0 error. I don't believe, because but there are some, maybe there's some 0.1 error, so on, but that's the detail. And okay, the third example, but now it didn't show the exact evolution, but it showed the fidelity. They overlap the exact solutions and the evolution of the quantum assist simulator to see whether it will follow the exact solution. So if the fidelity is 1, it matches the exact solution, but if not, it will have some error. So in this case, they use the same answers. As I say, it's 12 qubits and 200 layers, and you evolve this Hamiltonian, and you can think of this Hamiltonian after you use the Jordan-Wigner transformation. You can think of it like a tunneling of a fermionic particles between the first and last size of an n size, of a chance of an n size. And in this case, it simulates the n equals 10 situation. So you can see that now it can't use only the 1 moment state. You need to use more moment states. So in this case, they use 2 to cumulative 2 moment state to reach the fidelity of 1. And the fourth example is easy model, and in this case they simulate n equals to 8 situations, and they use the same variational answers. But let me recap you that it didn't have any classical quantum variable, because in this case there are some parameter you can see, but this parameter will not update because it didn't use any gradient descent. Maybe I need to remind you that. So in this case, this theta is just randomly choose, and then you follow what I say and didn't use any gradient on this parameter. So maybe there's an open question that how to choose these random parameters to get better accuracy. Maybe this is open questions. So in this case, they use k equals to 3 that can make this fidelity goes to 1 and it will success. But you can see that 2 and 1 and 0 is not enough. Yeah. And maybe there are some sorry. In this case, there's also further examples, but in this paper it didn't tell me a lot of details. It just showed the results, so maybe I need to skip it. But if you are interested, maybe you can send email to her writer and to get some more detail of this example book. But I will just skip it because it didn't tell me the detail. And also they also show the result of imaginary time evolution. Maybe 2 months ago, I gave some talk on imaginary time evolution, and maybe if you remember, the conclusion is equal to the natural gradient. But and in this case, you can also derive the differential equation on the imaginary time evolution cases, and you can also, and then you can follow the same algorithm into, but it's used is in the imaginary time evolution case, and you can see it will, in the k equals to 3 state cases, you will reach to the ground state of these cases. So yeah, it's imaginary time. It also shows the result of imaginary time evolution. And also there's some quantum crunch example, but if you're interested, you can see the paper. But what I want to say is that you can, in this algorithm, you use you use to k equals to 3 to reach the fidelity of 1. And if you're interested, you can see the paper. Yeah. So maybe he's go to the conclusion part, and in this paper they provide a quantum causal calculation that simulate the dynamical evolution of the quantum system. But the important part is that it didn't have any classical quantum feedback loop. So in practical, it's very good in practical in the perspective in the practical perspective. And second, the most important part is it didn't change the gate parameter, so it didn't have any baryon plateau problems, and also it has a systematic way to select the answers. So that is the conclusion. And there's an open question. I think it's not clear in this paper is how to choose a zero moment state, because it's just I think it's not it's just randomly choose a zero moment state and follow the Hamiltonian to construct the one moment state, but it didn't tell me how to choose the zero moment state depending on this problem. So, and also there's a very important part is what is the quantum advantage guarantee, and in this paper it also not clear in this paper. And the final part is there's also now the complex theoretical guarantees as well as the error in depth, and is also not clear in this paper. So I think these are three open questions in this paper, and the conclusion, as I say, is here. So maybe let me start. And any questions?
Okay, thanks. Any question or comment? Maybe okay. Yeah, please.
Hey, I have a sorry. I have a little question. Because in the classical part, you need to calculate the epsilon matrix.
It means maybe I go to this part. So you mean these two matrices? Yeah.
Yes, and in this part, you need to take the inner product of two states.
Yeah.
Is the two state inner product will take very small value. It will like you take very small. Can you?
Oh, it means the epsilon maybe is close to zero, and you cannot evolve this alpha t.
Yes.
Oh, it's a very interesting question. Maybe I need to think about it because I'm not very sure. But I think maybe it's a worst case because you choose the bad answers. Is that make sense?
Yes, but maybe the baryon plateau is the worst case in all these problems.
Oh, you mean
I'm not sure. Yes.
You mean if you use the algorithm in the worst case, you have say it also have some trainability problem.
Yes.
Okay. Maybe I can take notes on it.
Okay.
And any problem?
So maybe I miss your point. I'm wondering. You said you don't need a feedback loop, so you just arbitrarily choose the theta and fix it, and then you do the measurement to get a d and epsilon. Then you use the d and epsilon to do the differential equation calculation in classical computer.
Yeah.
And then that's done. So you just need to do once.
Yeah. You're right. Yeah.
So why? So your idea is to find the ground state of the Hamiltonian, right? So
it's a one example. Yeah. Well, most of the example is evolution of Hamiltonian, and for this example, maybe
Then what's the theta you arbitrarily choose play the role? What's the role of those theta you choose?
I think it's not very clear in this situation the rule of the theta because it only updates the alpha is outside the answers, the parameters outside the answers. It only updates this alpha in this case. This theta is in the answers, but it didn't evolve on this answer state. Do you know? The theta is implicitly in the phi I, but it didn't train on it. It only it only evolved the alpha t. It didn't evolve the theta. So I think it's not very clear the role of the theta in this algorithm.
Okay, yeah. Maybe I say this way. I guess the theta is the thing that can help you determine the answer's basis function. So it just helps you to determine the basis function arbitrarily chosen according to the theta.
Yeah.
So if you are going to find a better theta according to your question, then maybe that's the way to think how to define a better basis from the theta. That's my thinking.
Okay. But if you train on theta, that it will go back to the previous variational quantum algorithm. So I think you need some systematic way to choose theta, but it cannot you cannot train on it because you will train on it, it will go back to the previous variational quantum eigensolver and quantum simulation, and so that will meet the problem of the baryon protocols and quantum neural network training landscape. So maybe there's some random. You need to random set it, but not totally random. That is my opinion. Yeah.
Okay.
You need to depend on the problem, but not totally random chosen a parameter. Yeah.
Mm-hmm. Harvey, do you have other questions? Okay. Because Harvey still raised his hand, so I think he may have a question.
Okay.
Or not. Sorry, I have another question.
Okay.
I think once the Hamiltonian H is determined, then the decomposition into different U is also determined. Then why you show different K example? I mean, you showed several examples having different K and having different fidelity. What's the K you choose? How do you choose K? In the Hamiltonian decomposition.
You just add one. Maybe in this case, zero doesn't fit the exact evolution. If you just add one moment, do you make sense?
No. Can you say how do you choose the K one moment stay and 2 moments stay according to the Hamiltonian, for example?
In this example?
Yeah. How do you just how do you do it? The first term, the Hamiltonian is composed of 2 terms, which is U1 and U2, and then your K equal to 1 is just arbitrarily choose 1. U1 or U2. And K equal 2 is the combination of all 2 components.
Yeah.
Okay. So there will be 4.
So in this example, maybe U1 is just this state times all these parts plus this state times all these parts. But you can just times once. It's in the K equals to 1 situation, and K is equal to you need to times twice. For example, this term times twice, or this term times twice, and or cos term, and the cos term.
Okay, I see.
Yeah.
And you do all these measurement. That's what you mean?
What do you mean do all these measurement?
You need all these terms, and you need to determine the D or epsilon according to
for example, your K equals 2, you have 5 0 5 0 5 0 5 1 0 2 1 0 is all the combinations. In this case, also all the combinations. Yeah.
I see.
Yeah.
Okay, thanks.
and follow this we'll have previously we'll use Halama test, and in this paper they also show that if your Hamiltonian is a linear combination of polyterms, you can replace the Halama test to the direct measurements of the polyterms. Yeah, is a detailed part. Yeah.
Okay, thanks. And does anyone have further questions or comments?
Yeah.
Okay, if not, maybe that's it today. Okay, and thank you for everyone. And before we end, maybe Pedro, are you there?
Yes, I'm here. Can you hear me?
Yeah. Next week, the report will be given by your friend Robert, right? Roberto.
Yeah.
And so, can you host next Friday meeting?
Yeah, definitely. Yeah.
Okay. Then let's do it this way. And our working from home will till next the 14th, but I'm not sure how will it goes. Just let you know in advance. Okay. Okay, and thanks everyone. I think that's it today.
All right, thank you.
Okay, thank you.